Okay, so let's think about terminal velocity. And why we have terminal velocity. So, in this case, we're considering objects that are falling towards the Earth. And if we, in our booklets, we've got this image of a person falling, so it could be a skydiver. If they jump out of the plane, what is their initial velocity?
So they're jumping.
Well,
they're falling.
They're going to fall out of
Yep.
the plane.
Zero.
Zero. Initial velocity would be zero. What is their acceleration? 9.81. So acceleration is equal to, it's going to be due to gravity. It's going to be negative 9.81 meters per second squared. Negative because it's down. I'm going to say that down or up is positive. And if I were to represent this on a displacement time curve, and we're going to start them, so this is displacement. And let's just say it's 1,000 meters. Oh, let's make it 5,000 meters.
10,000.
You don't want them to die. Okay, so if this is displacement time, what shape are we going to expect this curve to have?
Like a curve.
Yeah, it's going to be curved. It's curved because we're moving with acceleration, but which way are we curving?
Are we free to all answer, or
Yes, we're all free to answer. Yes.
we'll be curving up that way because you slowly start to get faster and faster. No, you fast.
So you're saying curve this way?
Yes.
What do other people think about that?
Should it be reflected so they slowly go faster as they go towards the road?
Because they're coming down. If we're thinking that, like, if they're started, you've got the right idea, but we're actually going to end up coming down to Earth, aren't we?
Is the origin like ground?
Yes. So we're.
So Aiden forgot that he can fly further up
So he jumps out of the plane and
and goes up, not down.
Right. So we've decided we're actually going to end up going towards the ground, aren't we? But again, the shape, so Amy said reflected, which is a mathematical term. So is everyone happy that you know what that means? That we can think of it. We can think of it anyway in terms of this is time, isn't it, on this x-axis, and so I won't have travelled very far in the first second. I travel further in that second, and then I travel further again in the third second. I don't know what I said then.
Second, it just sounds weird.
Yeah, so that means that the gradient's getting steeper over time, doesn't it? So it starts out shallow, and then it gets steeper over time as we're accelerating. Now, for terminal velocity questions, we now have to consider air resistance. And so if we've got our person falling like that. What is air resistance? It's okay. Yep, Bria?
Like the particles in the air sort of hitting up against the person,
Yes.
as
Yep.
they fall.
So the person's motion is down, and air resistance is a force that works to oppose the motion. So it's pushing up against the person's body. And what happens though is that as the person's moving faster and faster, so if you're moving really quickly, if you think about each second and how many particles you're going to collide with, the faster you're going, then that's more collisions, isn't it? And so that's going to be more upward force until you get to the point where they are balanced. And when they are balanced, you have reached terminal velocity. Okay, so you accelerate as you fall out the aeroplane, you get faster and faster. As you do so, you're going to have more and more collisions with the air. And this is an opposing force until you end up at the point where those forces are balanced. What's that going to look like on my diagram? What shape is this going to be? At terminal velocity. If the forces are balanced at terminal velocity, what does that tell me about? Is it still going to be curved? What do we need to have for it to be curved? Acceleration. At terminal velocity, when the forces are balanced, we don't have any acceleration. Do we stop?
No.
No. So that means we must be travelling with constant velocity, mustn't we? Do you remember what that looks like on a displacement time curve?
So this is just a question about it. So in the sense that they're equal, does that mean that the air resistance is sort of equaling out gravity's pull on you? Okay.
Yep, so this one here is the weight force, or the force due to gravity.
Yep.
And then this one here is the force due to air resistance.
Yep.
And at terminal velocity, they are equal in magnitude and opposite in direction. Yep.
So if you're saying that the forces are balanced, wouldn't you be still?
No, remember that when, and this is I guess what I want to make sure we're 100% clear, that no acceleration means either you're stationary or you're moving with constant velocity. And that we know that when people are skydiving and then they reach terminal velocity, they keep moving, but they don't just stop in mid-air, do they?
That'd be cool.
It would be pretty cool, but that doesn't happen. Yes, yes.
It's like a straight
A straight line.
decreasing line.
Like,
Yeah.
we're going to have a straight line, aren't we? Because we've got constant velocity over time.
And you're not stopping.
And you're not stopping. What would it look like if we stopped? It would just be across like this. Yeah, that's not going to happen. Okay, it would be pretty cool if it did. But we know that that doesn't happen.
In the plane.
Parachute. Where's that next bit?
Oh. Well, I just want to ask another question. See how I've drawn my person here with, they're all sort of spread out. How do you think that's going to impact on the amount of air resistance.
Is that going to increase it?
Yeah. So we're going to have a lot of air resistance, aren't we? How could we, what could the person do to try and decrease the air resistance?
First.
The kid, make mistakes.
It's like you're going to die.
Yeah, do
Like
a bit of
an
a dive.
eagle.
Do a dive.
Yeah.
So if you're diving straight down, okay, that's the person.
Yeah, that's exactly what it looks like.
Then
It actually looks like a person.
then the area that they've got that they can interact with the particles in the air is much smaller, isn't it? So they're going to encounter much less air resistance. Now, if they dive from high enough up, they can still reach terminal velocity. But what could you predict about the terminal velocity for this person, this brave woman? This is madness as far as I'm concerned. But what is their terminal velocity going to be like compared to this person's terminal velocity? Yes, Aidan.
Well, first of all, because they're going to get to a faster terminal velocity, a greater terminal velocity, so then their acceleration they'll have a longer acceleration because they're accelerating to a greater speed, and then they'd be, they're going faster because there's less air resistance.
Yeah. Yep. So this person here would accelerate for longer because it's going to take them longer to reach terminal velocity, and then they're going to have a higher terminal velocity.
Sorry, if you were in that and then you suddenly went out to this, would the air resistance break your arms or anything? Like if you're going from that, you're real fast, and then with that.
Well, I think you'd feel it for sure.
Surely you wouldn't be able to put your
You'd
arms
struggle
out.
to be able to get your arms out.
You might. It might be a bit of a struggle. Yes, that's right.
Imagine your face with that.
Okay, now.
We put our hands up at the same time. You go first.
Where's their back? Where's like their parachute on their back?
Yeah, I was just going to draw
No,
their
that person's
parachute.
just free falling.
There we go.
So when like a spaceship comes back, and or like in the movies the meteorites come in, when they get like that fire thing, is that because their like velocity or whatever acceleration is so great, like that is it like reacting with the air particles, or like what's happening?
Yes, there's friction. Yeah.
Is that because there's so much friction that the friction heats up and then it gets so hot that it just...
I think there's a little bit more to it than that, but yes, there's definitely that aspect to it. And if you look at the world, and we've got the atmosphere, there's also an entry angle that you need to get correct, because you can, if you come in at the wrong angle, you can just bounce off the atmosphere.
Rejected.
Yeah, that's
Not today.
that's the meteor that the atmosphere rejects.
What was that, sorry? I missed that bit.
The angle needs to be right. You need to have the correct angle for entry in through the atmosphere, because otherwise you can bounce off the atmosphere.
How would that feel if
So
you
if you're a
just
spaceship, you
bounced?
come back, like you only got a little bit of fuel and you get the wrong angle.
You're stuffed, Aiden.
You just see yourself like flying away, like, what on earth?
And we also see, like there's a lot of particulate matter that comes into our atmosphere, and it burns up, doesn't it, when it comes in, because it's meeting that friction of the atmosphere.
Is that angle has to be straight on? Or
No. Well, if you're an astronaut and you want to survive, then you also don't want to be coming in. You want to be coming in slow enough to survive the re-entry. That's because you might not only want to land on Earth, you want to be alive when you do so.
You go through the atmosphere, but you miss the actual Earth itself.
So with the Apollo missions, they landed in the ocean deliberately because the ocean then allowed them to have a softer crash landing.
So, is there like a certain level of force that our bodies can withstand?
There is. Yes.
So, if you were in like the dude that's like straight diving, would he, like, what would happen if you got to that force? Would you just break apart, or would you like face rip off, or?
So far, I haven't seen any YouTube clips or whatever of anyone's faces ripping off, but your bones could break. It's more about the impact, and so this, at the moment, we haven't landed. So this person here, they're in deep doo-doo if they're going to keep going like this, aren't they? Would not recommend that.
Go straight into the water.
This person is going to open their parachute. Okay, so when you see somebody who's skydiving, you see images of people skydiving, it looks like they go up, doesn't it? Do they go up?
They just stop.
They slow down.
They decelerate.
They decelerate. It looks like they're going up because they're slowing down, but they're still actually travelling towards the Earth, aren't they?
Would there be an instant in time when they aren't actually moving from that? When they open their parachute, would there be one time where they're not actually moving?
The only time they won't be moving is when they're on the ground. They'll stop moving then. Yeah, because the gravitational force is acting on them all the time. The gravitational force was acting in the aeroplane, but because of the normal force of the floor of the aeroplane, they didn't fall down until they deliberately fell out the door hole, and then they're acted upon by gravity until they stop. We're assuming this is not Iron Man, okay? No jetpacks or anything on here. We're just it's just a body with a parachute.
Is there a correlation between the weight and the terminal velocity?
Yes, the mass is going to impact on how fast that. So it's more to do with the surface area in actual fact. The surface area is the big contributor to terminal velocity.
Surely there was
Because all objects will fall at the same speed, won't they? They all, if we drop our objects and we ignore air resistance, they land at the same time, no matter what the mass.
But if surely there was like some astronaut or someone who like parachute or jumped from like orbit and made it down, he wouldn't. Surely he'd burn up though. Like how come spaceships and that burn
It's
up?
actually really, really cold up.
But as you come down and the friction, like how come?
You wear a suit.
But how come if you're parachuting, how come you don't burn up but a spaceship does?
Well, parachute, like we're not very high off the ground here. And like I said, it's actually cold. So the time involved in somebody skydiving landing compared to a spaceship's re-entry, they're quite different. And the speeds they're travelling at and etc. are quite different.
The spaceship's going much faster.
Yes. Yes.
Right.
It's faster and it's bigger.
If we were going faster but the same mass, would we burn it?
I'll have to have a think about that because, like I said, it's actually quite cold up there, and so we need to go. We need to talk about the course material, and then we can deviate on to that later. But I'm just mindful that I'm actually recording this and talking about stuff that you don't need to know. Okay, so we've established that this person is not going to go up when they open their parachute. But they are going to slow down. What is that going to look like on my graph?
A sort of a steeper, well, not steeper, but more of a curve than what the first one that we had, because they're sort of slowing down.
So like a flatter curve.
A flatter curve. But we agree that we're going to have a curvy bit, don't we? It's going to be a curve. What way? Is it like this or is it like this?
Wouldn't it be the same as the first curve? Like it'd curve a bit, and then once you finish decelerating, you'd get to a constant velocity as well with the parachute.
When is the deceleration the greatest?
When you open it.
Doubt, isn't it? Because our deceleration was increasing.
That was mine, it fell off the top.
Okay. I looked at you first.
So it would be going like that.
Like an L.
Like an L.
Yeah, a bit like that.
Do we think that could be right? We think it might be that shape. Or
Is it going to increase to try and reach? Isn't it going to continue to increase to try and reach the terminal velocity of with the parachute?
it is going to need to. So we've got some rapid deceleration,
You know.
and then we've got. Then we're going to be approaching terminal velocity again, aren't we?
Yeah, so isn't it going to be that middle one? That one?
This one. Depends on what kind of diagram you see. But the area here could have a bit of this for that initial opening of the parachute, or it may not. But yes, we are then going to have a new terminal velocity as we are going to be speeding up towards the ground again, as we are encountering more air particles. And how is the slope going to relate here to when we reach terminal velocity? What's the second terminal velocity going to be like compared to the first? What's it going to look like?
It's flatter.
Flatter. Well, so it's not going to have. It's going to have a shallower gradient. And then hopefully we land here and we're all smiley because we slowed down enough to not break our legs. Okay, so a couple of things about thinking about. Terminal velocity means that the forces are balanced, no acceleration, but we're still moving in this case. The faster we move, the more we interact with the air particles, and so the bigger the force vector from the air resistance, which is always going to be opposing your motion. We're going to assume that, it's not like there's wind blowing you around from left to right sort of thing. We're not worrying about that. We're just only concerned with up and down. Is that okay so far? Yeah? Any other questions?